Hiya Pirates! Today we're going to do a whole bunch of more math. This one is to do with bond energy sample problems. So a couple of things to remember. If you are looking at a bond, whether it's this triple bond or this single bond or whatever, remember just a couple of things about it. If the process is trying to break a bond, remember that the energy goes in to breaking a bond, or it is a positive value. If, however, the bond is being made, then the energy comes out. So if you are making a bond, then the energy comes out. It's exothermic, or it is a negative sign. Regardless of whether it's positive or negative, breaking or making, it's the exact same amount of energy. It's just a question of the directionality of that. So I have given you this chart. And this chart here has some approximate bond energies of single, double, and triple bonds. Why does it say approximate? I don't know. It's one of those things where depending on what source you use, you might get a slightly different value. So for instance, that 436, I've seen everywhere from 436 to 432. So if you're using a different source than this worksheet here, you might end up with a slightly different answer, or even a considerably different answer, depending on what source that you use for things. So my recommendation is that you use only this source to do these problems, or use the information that's given to you in the problem. You don't have to memorize any of these numbers that are there. So again, if you are trying to break a hydrogen-hydrogen bond, then it is going to cost you 436 kilojoules of energy. If you are making the same, you will get 436 kilojoules out of it, or it'll be negative. So really the question is can you add up the amount of energy it took to break everything, add up the amount of energy it took to make everything, and then compare those two amounts? Or if you'd prefer, there is a simple equation that goes along with some of this stuff, and the equation is that the delta H of reaction is going to be equal to the sum of the bonds of the reactants minus the sum of the bonds of the products. So you're going to add up the reactants, and you're going to subtract the products, and you're going to go to town there. The other way to look at it is where you add them up and make sure that the products are negative. I don't know that it helps you any better that way. Basically, what you're going to do is you're going to add up everything that is reactant. That's going to be a positive. You're going to add up everything that is a product. That's negative. Or you're then subtracting the bonds of the products. So let me give you an example here. This is just one carbon monoxide and one chlorine. So if we were to look those guys up, this is a 1075 and this is a 243. So the bonds of the reactants here is going to be 1075 plus 243. That's your reactants. And then we're going to subtract from that the bonds of the products. And the bonds of the products are 330. But remember, there's two of them there. And then 803 for this guy. Again, all those numbers are coming from this bond energy chart here that I gave you. So this is now 803 plus 2 times 330. So assuming I have done my math right on all of this, I got an answer of negative 145 kilojoules for my final delta H of my reaction. And because it is exothermic, it must mean that the bonds of the products being formed are more energetic than the bonds of the reactants being broken.